we started with Tidymodels, and we discussed about the ecosystem of Tidymodels. Okay, so we spoke about the resampling package that is used in splitting the data. We spoke about we discussed also about the parsnip, the recipes, and the DAOs and other stuff. Okay, so yesterday we were able to do a logistic regression, and on categorical outcome, and we were able to set our develop our model in terms of fitting the model, okay, and then populating the model, and after running the model, we were able to evaluate it. So we evaluated the performance of the model using the receiver operating curve, or the ROC curve. And then we also spoke about the area under curve, which is a single number that determines how effective the model is performing, right? So that was what we did yesterday. So today we will build upon what we did yesterday. Yesterday we did logistic regression. So this morning, before we go into feature engineering, we just want to see how the model also performs in terms of being used to do linear modeling, right? So we'll just, most of us are conversant with regression, so I wouldn't spend so much time there, but just for you to know how we use the Tidymodels to do regression, linear regression, where the outcome variable is numeric. Okay, yesterday the outcome variable was not numeric. All right. Okay, so it was a categorical outcome. Okay, so we will look at that. We'll briefly look at how we can use the Tidymodels in a situation where we have an outcome variable that is numeric. So after that, then we'll look at the feature engineering, pre-processing steps, how we can transform our data to either do prediction on a numeric variable or a categorical variable. All right. Okay. So I sent. Let's go to our R studio. But before then, I can share this with you. Let me share the slides first. Okay, so let me just quickly run through this one. We discussed yesterday. Okay. So today we'll look at pre-processing steps for model fitting, transform numeric variable by dealing with multicollinearity. Okay, how we create dummy variables for nominal predictor variables, and then we will do a complete modeling workflow. All right. So yesterday we spoke about the components of the Tidymodels ecosystem. So we are conversant with this already. Okay. So we spoke about the resampling package. We spoke about the recipe package. Today we'll do more of recipe and baking. Okay. All right. So we introduced recipes package, the parsnip package, the tune and DAOs package, yardstick package for model evaluation. All these things we discussed yesterday. And also, I made you to understand that the supervised machine learning are in two categories. Okay, so we have the regression models and the classification models. So yesterday, we dealt with one of the classification models, right? So let's look at a simple linear regression model. For instance, if you want to look at the relationship between these two variables, you understand the equation already, where the beta naught or beta 0 is the intercept, and the beta 1 is the coefficient, and then you have your x as well. All right. Okay. So basically, a simple linear regression, you will have this. If they are all correlated, you will see that they move together on this line. Okay. So you are quite conversant with this already. All right. So in using the parsnip package under the Tidymodels, it's basically the same thing, similar thing we use when we are using base R linear LM function. Okay, so you just have the outcome and then the tilde, and then you have the predictor variables on your right. Okay, so we are conversant with this already, and the shorthand notation is the outcome variable tilde dot will bring in all the predictor variables or the independent variables. Okay. So the parsnip package, we use that in specifying a model type. Okay, yesterday we saw how we can specify the model type. Okay, specify the engine and also the mode. All right. So if you will notice yesterday when we're doing the logistic regression, we set the engine at GLM, that's general linear model, and then we set the mode as classification. Okay. But when we want to do linear regression using the Tidymodels, we set the set engine to LM, okay, as linear modeling, okay, and then we set the mode to regression, okay. So let's use this for let's import the home sales data set I sent to you. So let's go to our R Studio. Okay, so just run your library for the Tidymodel, set your siege, and then specify your directory. It makes things easier. Okay, so the data sent to you is an RDS file. Okay, so we use read RDS to open it. Okay, and our data was home sales of RDS. Okay, so let's name this one. Okay, so let's read this into our R Studio. Okay. Okay. Okay, let me check where I have this. Just a minute. It's a long part. we are good to go. Right, so let's have a look of sales data.
Record.
All right, so here you can see the selling price. I think we've dealt with a similar data set, but not this particular one. Okay, so we have the selling price of the houses. I think when we're doing classing, but that's a bit different from this. So this is the selling price of the houses, the age of the houses, the number of bedrooms, number of bathrooms, square living area, um, other information, square foot measurement for other areas of the house. There, so you have the one for the living room. You have the one for basement, and then other areas, and also including the number of floors. All right. So all these variables come together to determine uh, the price of the house. Okay. So we just want to um, predict the house prices. All right. So let's do our data partitioning. So I'll call this so we have our initial split, isn't it? Our initial split. So our initial split, we want the home sales data. Okay, home sales data. And let's use a proportion of 0.7. That is okay. And remember the strata argument. Okay. So if we are predicting the house prices, what do you think should be the strata? The strata, what should it be equal to? What do you think? Should it be equal to the size of the living room or the number of bedrooms?
The selling price.
The selling price. Excellent. Okay. I just wanted to trick you. So okay, so selling price. Wonderful. So it's always the outcome variable that we use for the stratification. All right. Okay. So we have our home for this home split. So that's for the splitting of the data. Okay. So let's run this. Okay. So now that we have stratified the data, let's populate the training and the test data. Okay. Okay. So we take our home split. We take our home split and then we pipe that into the training function. Okay. We pipe that into the training function. So let's call this home training. Okay. So let's run this. And then remember that it has the 70% already in memory. All right. So we leave this as blank and then it will take the 70%. So once it's done the 70%, it also has in memory that the test data should be 30%. Okay. So let's populate the test data. Let's name this home test. Okay. And this one becomes testing. We pipe that into the testing function. Yeah. Please, if you have any question, you can stop me anytime. Okay. So let's run this. So now we have our test data, and then we have our training data. Okay. You can even take a glimpse of our test data and then the training data, the home training here. So let's take a glimpse of our home training. So our home training comprises 1,042 rows. Okay, let's see our home test. Okay, that's 450. Okay, that's fine. So now let's initialize our linear regression object. Okay. So this is our linear model. So here we are using linear regression, okay? Non-logistic, so linear.
Hello, Nana.
Yes.
Please, can I show you my screen? I have a problem reading the
No
file.
problem, Ernest. Share it quickly. Let's move on. And what is the problem?
So,
Enlarge it a bit. It's too small.
so
Yeah.
I'm trying to read the file, but this is what I get.
You get what? Can you read it? Your fonts are too tiny. I can't. I'm struggling to see.
And how do I
Can't
get
you
the font?
increase your fonts? Yes. Go to tools. Go to tools and then global. Yeah. No, not view. No, go to tools. Tools, not view.
AG plan ENI.
And then go to global options. Yeah. Then look at appearance. Yeah, you can change the font here.
Is it better?
Okay, yeah, it's better.
Okay, so I'm
Yeah.
trying to pick the file, but it's
Yes. Is it in the working directory where you picked it? Check
yeah.
whether it's in the working directory. Check it well.
So it's here.
Where is it?
There it is.
But I'm seeing it in desktop something. I don't know where it is.
So desktop DDD. So this is desktop DDD.
Okay. Okay, so you copy the properties again. Copy the properties again.
AG plan ENI.
And then copy the file path. We run it again, let's see. So when you set the working directory, what does it say?
It works. It's
That one works.
yeah, this is the working directory.
Okay. And then when you read it, what does it tell you?
That's why I get the error in
It cannot open.
yes.
But it says that there's nothing in the directory. Hmm. Okay. Do you know what? Go to No, that one cannot open it.
So there's a file.
This is the
I'm
one.
also having
Are you also having the same problem? Is someone
yes,
else having the same problem?
So it seems when you are saving from the WhatsApp and you don't save it well, it will save as a .gs file. So go to your WhatsApp file and click save to downloads directly rather than the automatic download. That's how I solved mine.
Okay.
Please again.
No, I was saying for mine, what I did was when I was downloading from the WhatsApp, the automatic download gave me this, but I had to click save to downloads again, and that one gave me the GZ version. Or else for Windows, you could try to change the extension file directly. Rename. No, it shouldn't be .gz. RDS, right? That's the extension. Is it RDZ or something like that?
Okay.
Yeah, it's RDS.
Yeah, now it works.
Yeah.
Fantastic.
All right.
Thank you very much. Nana, thank you.
You're welcome. Okay, so let's go back to where we were. So now we want to specify the model we're using. So we're using linear regression. Okay, so we pipe this.
Nana, please your screen.
You can't see my screen.
Yeah.
Okay. Okay. So let's pipe this linear regression. Okay, let's pipe this linear regression to our set engine. So let's set the engine. So set engine. Okay, so here we are using LM, linear modeling, not GLM. Okay, then we pipe this also. Pipe this also to the mode. Okay, so set mode. So our mode is regression. Okay. So if this were to be a categorical outcome, what would have been the mode? Your question? Can someone answer? If this were to be here, the outcome variable is numeric because we want to predict house prices. Supposing that it was a categorical outcome, okay, like yes, no, that kind of thing. What do you think the mode should have been set to?
Classification.
Wonderful, wonderful. So you are now getting it. That's good. Okay, so we run this. So we are fine. So now let's fit our model. Train the model. With our training data. Okay, so we have our linear model here. We have our linear model. Okay, so now we want to determine the the regression equation. Okay, so we normally pass this to the fit function. Okay, the outcome variable here we are saying is the selling price. Okay, tilde. You know the notation, so we can just put everything here. Okay, and then our data is home training, because we are using the training data set. Okay. So let's call this LM fit. So we have fitted the model with our training data. Okay. So let's run this. Okay. See the information we have in our LM fit. So this basically gives us information as to we have information as to the coefficients of all the variables. Okay, you know how to interpret it, so I will not waste much time. Okay. Now, once we have set the training, okay, we need to transfer this, okay, to the test data so that we can do our predictions. Okay, so if we want to predict our house prices, now that we have trained the model, let's predict our house prices. Okay, so we use the predict function. We use a predict function. Okay, so it takes what we fitted in the model, the trained data, okay, and then this new data. So whatever we have done, the trained data is transferred to the new data. Okay. Okay. So here we specify that it should be worked on the test set. Okay. The test set is the home test. Okay. So let's name this home predictions. Yeah. Okay, so we are predicting the house prices. We use the predict function, okay? And then we base that on the trained data, okay? All right. So whatever information we have put in the model, okay, pertaining to the training data is what will be used for the test data, okay? So it goes to the test data and then it uses this function, this equation that we have here. All right, so it's the same thing that it will do in the test data. All right. All right. So if we are to print this, print this, we will have the predicted house prices. So to just print the column for the predicted house prices like we saw yesterday. Okay. So we now have to combine it with the other variables to compare the actual with the predicted. All right. So let's combine the test data with the predicted. Okay. The prediction. Okay. So we have our test data, that is the home test. home test. Let's pipe that and then select the one we are interested in. We are interested in the you can select the selling price variable. You can select the selling price variable, home age, so everything will be there. Okay, home age, square living. In terms of the living area, okay, the square foot measurement. Okay. All right, so we select these three variables that we are interested in. Then we pipe that, okay, and then combine this. So we have selected this, and then we combine it with the home predictions that we've made. So we use the bind poles function. Bind the columns together, okay? So home predictions. Yeah. So let's call this home test results, okay? Okay, so when we run this, let's call the home test result. We should see the actual as well as the predicted values, okay? So let's view it so that we get a more rounded view. So here, so we have the actual selling price, which is this, okay? This is the actual selling price, and this is the predicted selling price, okay? So this is the actual and then the predicted. Any questions so far? Any questions so far? So we have made the predictions, but how effective is our model? Okay, so let's evaluate our model to see how it is. Yeah. So model evaluation. Now, when it comes to regression, a common metric, unlike the logistic regression where we use the area under curve as a metric for model evaluation, all right? When you are dealing with numeric outcomes, okay, typically linear regression models, we cannot use area under curve, okay? So the common metrics we normally use, we have the root mean square error. Root mean square error. Or RMC. Okay. Or the R squared metric. Okay. Okay. So we have these two. Okay. We also have the adjusted R squared. Okay. So is the R squared metric. Okay. So let's see how we can use these two to determine the the effectiveness of the model. Okay. So let's calculate, for instance, the first one, the RMC metric. So it is a very simple process. It just uses the RMSC function, all right? And then the truth or the actual data. Okay, so you have this truth argument that refers to the actual data. In the actual data, we are looking at the actual selling price, isn't it? So the truth is the selling price. Okay. And then the estimate, our prediction, is equal to, if you check here, you see that and the variable for this is dot pred. Okay, so that's what we use for our estimates. So we have the selling price, this is the actual selling price, and then this is our prediction, dot pred. Okay, so our estimate is dot pred. Okay. Now let's run this. Selling price is not found. Okay. Run the mistake. Let's see how the selling price is found here. Okay. I needed to pipe it to the main data set. Okay. So we are taking all this information from the home test results, isn't it? Then we pipe that one into the function. Okay. So the home test result, this one, okay, gave us this. Okay, give us all this. All right. So we take that and then we calculate the root mean square error. Okay, so the first argument is the truth, that is the actual selling price. Okay, so that is equal to the selling price. And then the prediction, okay, this is our predicted selling price. Okay, that is dot pred. Okay, so that is the estimate. So let's run this. So it tells us that our root mean square error is 40,261. So if you remember what we did last time in our mathematical foundations, basically what you want to do is to reduce your error. Okay, so this one on its own doesn't really tell you much, all right? But you can use it, let's say, if we are to add another variable or even remove another variable from this equation, okay, from this equation. Remember that we use all the outcomes, okay? Let me go up here. So we selected this, all right? We selected this. Supposing we leave some out or we add more features to this, okay? And then we calculate our RMSC and it is, let's say, 15,000. Then that model is better because it has less errors, okay? So the bigger the RMSC, the poorer your model, all right? So it helps when you are comparing 2 models or 3 models. We want to take the one with the least RMSC, okay? Please, any questions about the RMSC? Okay, all right. Let's look at the other metric of R squared. Okay. The R squared metric. Please, are you following? Yes, yeah. I've seen your hand raised.
Yes, sir. Please, I just wanted a clarification on where we selected the dependent, the other variables, the dependent ones. Is that at the fit area or when we were piping the, when we were trying to do the home test results?
Okay, let me go up here. Was when we were fitting it here. You see.
Okay, so this is where you determine which variables you select to affect. Okay.
Yeah, so there I selected everything.
Okay.
So when you use the dot, I mean that you are selecting all the predictors.
Okay.
All right. So let's any other question? Any other question? That was a good question. Any other question? Any other question? Okay. Let's look at the R squared metric. It's the same thing. Okay. So the only difference is that we use RSQ. Okay. So let's copy this. So the tidy model really makes things very simple. RSQ. Yeah, that's it. So when we run this, so the RSQ is looking at a situation whereby the nearer your value gets to 1, the better your model. Okay, so it's not like the RMSC. Okay, so here we have 0.75, which is quite good. Okay, really quite good. So or towards 100%. Okay, so our model is doing 75%. All right. So these are the some of the metrics you can use. Okay, you can use other R applications to calculate the adjusted R squared and stuff like that. Okay, but for tidy models, these are the two main ones to calculate for. Okay. Any question? And even this one, you can actually plot and then see the performance of the model. Okay, you can plot and then see the performance of the model. Let's try and do that. So let's create an R-square plot of the model performance.
Hello, Nana.
Yes.
Is it okay if the figures vary for the R square metric and the root mean square error?
What do you mean by if they vary?
I am getting higher figures.
You are getting higher figures. So for your RSQ, what did you get?
So for my RSQ, I got 0.751.
Okay, so it's 75%. It's basically
Yes, please.
And then your
Okay.
RMSE is what?
It's 41,973.
Okay, all right. So sometimes these small differences could be as a result of the setting of our seed, okay? But it is negligible in terms of the interpretation of your result. All right.
Oh, okay. Okay. All right. Thank you.
So let's create an R-square plot to see our model performance. Okay. Okay, so we can use, and the good thing too about Tidymodels is that it has ggplot in there. Okay, so you don't need to call ggplot from the library. Everything is in there. So it has dplyr, ggplot, so many packages. Okay? Apart from, in addition to the, how do you call it? The parsnip and then the resample and then the recipes. So we can go straight to ggplot. So let's plot our data is home test results. Okay, and then what we want to do is to plot the actual versus the predicted. Okay, so our actual is a selling price, and then the predicted is dot pred, isn't it? So for our aesthetics, the X will be selling price. Selling price, and then our Y will be dot pred. Yeah. Here we add the geom point. Okay. Let's look at the transfer. We can set our alpha at 0.5. You can increase it if you want. To embellish it, okay? Plus, we want an AB line, okay? So I'll do a geom AB line here. Okay. Let's specify the color to be blue. You can choose any color you want, okay? And then the line type. There are so many line types, okay? Either dots or line type 2. And ggplot has this special function called chord of spread. Okay, so what it does is that it helps you know the predicted. It's able to calculate and know the predicted versus the actual. Okay, so it's a function. So let's look at our labels. So our X is equal to actual home selling price. Let's put this in. And then our Y is the predicted, isn't it? Y is the predicted selling price. Okay. All right. Let's see. Yeah, okay with the plot. So we have our AB line, we have our predicted selling prices versus the actual selling prices. Okay. From what I can tell from here, you realize that for house prices that are kind of that are below 400,000, you see here, 400,000. So where you have the diagonal, okay, is where the actual and then the actual and then the predicted are the same. Okay, so where you have the diagonal line is when it is the same. All right, so if it is above it, that means that it is over predicting. If it is under it, that means it is under predicting. Okay, all right. So for if you look at the first one, for house prices that are below 400,000, you see that the model tends to overpredict, isn't it? All right. The model tends to overpredict. And then when you look at house prices that are sold for 600,000 or more, okay, you come here, 600,000 or more, you see that the model tends to underpredict. Okay. All right. So this indicates that you have to add more predictors to your model, okay? All right. Or you can look at other modeling techniques to help you use this particular model. So, and it was explained by the R squared, it was just 75, okay? So if it was something that was about 90%, you will realize that the over prediction and then the under prediction would have reduced significantly. Okay, so the model is fairly good, but it's not the best, especially when it comes to under predicting of some value. So for house prices below 400,000, you see that it is above the line. There are so many dots above the line. It's over predicted. Okay, and then when you come to 600,000 and above, okay, you see that the model is under predicted. Okay, all right. Any questions? So these are some of the insights you can draw from the performance of your model. Okay. Any question? Any question? Okay. We go for some. Let's go for 8 minutes break. Okay.
Hello, Nana.
Yes.
Please, what about the house prices within the 500,000 range?
So with the house prices within the 500,000 range, you see that some of them it's a bit scattered, but you see that how do you call it? Basically equal proportion are being under predicted and also over predicted. Have you seen? So when you have it, you want to, as much, you remember the GGQ QQ plot when we're doing the regression. Okay, you want it to be, you want all your models, your data points to be as close to the diagonal as possible. All right. So so you see that we even for 500,000 thereabout, equal proportion are being under predicted and also over predicted. Okay, but the tail ends is where you really see that majority are being under predicted or over predicted. Okay, but in between the two, it is like equal proportion is being under predicted and over predicted. All right.
Thank you very much.
Okay. So let's come back at get something hot to drink and come back. Let's give us let's come back 9:45. Okay, 9:45.
And a quick one.
But I'm still here. So anybody, just a minute. I'm still here. So anybody who wants to ask a question, you can do that. But you can have a short break and come back at 9:45. Yes, please go ahead.
I was asking whether our main break will come like the 30 minutes break, because that will be at 10.
That will be at 10.
Yes.
Okay, so should we continue and then we go for our main break?
Yes, let's do that.
Yes, ma'am.
You want that? Okay, all right. All right, okay. So let's continue. No, but you go for some 2 minutes and come back. I've set your mind up for the break. Just get something quick to drink and come back. Okay.
Okay. Then.
No problem.
Sure,
10 o'clock, we'll go for the break.
That's good.
We'll be here in 3 minutes. Okay, please.
Please, sir.
Yes, Christiana, how are you?
Please, can you move up to data partitioning?
Okay.
Thank you very much. Please, can you go up a little? No, like down. Like I want to see. Thank you. Hello, sir.
Okay, Christiana, yes.
Please, sir. When I try to run my when we get to data, is it populating test is it training sets? It's telling me home split not found. I've tried, it's the same, but it's not allowing me to.
Home split. Did you split it? Did you do the data partitioning? This one? You do the initial
Yes,
split?
sir. Yes,
And
sir.
it's a home split not found. Did you name it home
Yes,
split?
sir. Pardon me, sir.
Did you name it home split, the data partitioning?
No.
Yeah,
Okay.
so if you didn't name it home split, then use the name that you use. Okay.
I did not use any name at all.
Yeah, but you need to use the name. Other than that, you cannot populate the training data set because you are piping it into the training function.
Yeah, I've realized that.
Okay. All right, so got that one.
Enabling is asking. Thank you very much.
Okay. All right, guys. So let's move on to the feature engineering stage. The focus of our lecture. So let's go back to our slides. All this. Can you see my slides, please?
Yes, sir.
Yes.
Okay. So what feature engineering is basically is the process of transforming data to a format that is suitable for machine learning algorithm. Okay, sometimes the nature of your raw data might not be suitable for machine learning purposes. Therefore, it is imperative that you transform your data, okay? Okay, you look at your features, you look at your attributes of the data. Okay, so the features really are the columns, right? How you transform these columns, all right, to make it suitable for machine learning purposes. Okay. So for in the area of Tidymodels, the recipes package is what does the feature engineering. Okay. Now, what it does is that it assigns rows to the columns of our data. Okay, so a column could either be an outcome variable or it could be a predictor. Okay, all right. So it assigns various rows to our columns of our data. It also defines pre-processing steps, okay, and the data transformations that we need to do. We'll look at various types of data transformation. And then when it has finished, it applies whatever transformation it has done, okay, to our training data and also to our test data. Okay. So first of all, it assigns rows and then defines pre-processing steps, okay, for every task that we are going to do, every kind of data transformation. After it has done that, then it applies these transformations to both our training data set and also our test data set. And then we go on to make our prediction. All right, so let's see how the workflow goes about. Okay. So here, basically, we are specifying your variables, okay? And then so this is the recipes package, basically, okay? So we define the pre-processing steps, and then we use a function called step, okay? You will see them shortly, okay? Whenever you use the step function, these are the pre-processing steps it is taking, okay? All right, and then what it does is that we train our transformations. We need to train them before we apply them. Okay, so we train them using the prep function. Okay, you see the prep function here. Okay, and then after we have done that, we apply all these pre-processing steps to our data set. When I say data set, I'm talking about the trained data and also the test data. And we use that using the big function. All right. Any questions about these steps before we go on to look at actual data? Yeah. So each column, like I say, it specifies the variable type and row. So each column could either be an outcome. So you have various columns in your data set. Okay, what is your target? So whatever target you have in mind, whatever you want to predict is your outcome variable. And then any features that you select to help you do the prediction will become your predictors. So they will be playing the predictor roles, okay? Whilst others, one column will be playing the outcome role, okay? Now, these variables could either be numeric variables or they could be categorical variables, okay? The same thing, your outcomes could be numeric variables or they could be categorical variables. Remember yesterday when we were dealing with a categorical outcome, we used logistic regression, okay? This morning, we used a numeric outcome and then we used regression, normal linear regression. All right, okay. So based upon the outcome variable, okay, will determine some of the transformations that will be possible. All right, okay, so we'll see all of that. Okay. So let's go into R, and then we want to do our transformation side by side with the slides so that you follow it accordingly. Okay. So the least data set that I sent to you, okay, let's import it into R Studio. Okay. So let's go to our R Studio. And then let's import our list data set. Okay. Please remind me when it's 10 o'clock so that you can go for your break. Okay, so I have set my working directory already, so I just need to just read. It's also an RDS file, okay? So read your RDS. So our leads .rds. So let's call this leads. Yeah. Kindly mute yourself, okay? All right. So okay. Let me check it. Please, can you inform the person whose mic is on to kindly mute? Yeah.
Okay, Alaya, please mute.
Getting similar.
Please note that the file is leads, not lead. S after the lead.
Oh, okay. Right. Yes. Thank you. Let me have a glimpse. Okay, that's fine. So let's move on straight to the data partitioning. Okay. So we have our initial split. Our data set is leads. Our proportion 0.7. Our strata will be purchase, isn't it? This is our outcome variable. Okay, so we use it. We want to predict. So okay, I didn't tell you about the. I'll tell you in a minute. So let's view. Let's view the data sets. Okay, so what we have here is we have visits to a particular website. Okay, so we have the total visits of a person, the total time they spent on the website, the pages they visited on the website, the total clicks they made. Okay, all right, who kind of recommended them, all right, and then the location of the person. Okay, so person could be in Takoradi, Accra, Kumasi, Koforidua, and other places. Okay. And then, so now we want to predict whether if somebody visits the website, they will purchase a product. Okay. So our outcome variable is purchase. Okay, and then we have other predictors. Okay, so this is in short, what the data set is about. Okay. So let's partition our data. So our strata will be purchased, isn't it? Our strata will be purchased. And then let's do least splits. Yeah. Okay. So now that we've split the data, let's populate both the training and then the test data. Okay. Yeah. So we have least split, and then we pipe that to training function, isn't it? So this will be our least trading. Okay. Let's do that for our test data. So with this one, we use least testing, okay? For our test data, least testing. Least testing, and then we pipe that into our testing function. Yeah? Okay, so let's run this. Let's run the first one. This is our testing training data, and then this is our testing data. Okay? Yes. Are we okay? Are we okay?
Hello, Nana.
Yes, please go ahead.
Yes, the lead split, when you go to the top,
The initial split.
yeah, no, not the initial split, the lead split, the data partition. You did it
Okay.
right.
Okay.
So calling it over here would probably
Okay.
give an error.
Okay. Thanks. Yeah. Yes. Any issues? Any questions? Any questions? Okay, so let's have a look. Let's have a look at the data again before you go for the break. So you see that, so this is the whole data set. Okay. So purchase, no, so this is a categorical outcome, that's fine. Number of visits, we have this column. Total time spent on the website, we have this. And then pages per visit, we have that. Okay, total clicks. Now, see something. You see the total time. See that the numbers are very huge, okay, as compared to the other ones. So when you have it this way, it can really bring some variability within your model. The variability within your model could be huge, okay? So one of the ways you do this is to try and reduce this number, okay? We want to reduce this number to something that could be comparable to the total visits and then the pages per visit, all right? So one of the ways to do this is to find the log, okay? Find the log of this particular one, okay? We can actually find the log base 10 of this, okay, to reduce the number, okay? To reduce the number to something that is comparable to this, okay? So one of the things we would do, let's do that before we go for break so that when we come back, we do other stuff. Okay, let's reduce the number for the total time spent. Okay, so how do we do that? First of all, we need to build a recipe of it. So let's reduce the total time figure by applying a still base 10 to be specific. Okay. So let's see how we do this. So normally you pass this on to, we use the recipes package for that. So recipe, we know that the equation is purchased tilde all the predictors, okay? And then we are taking this data from our, we are training it, okay? Okay, we are training it and then we are taking it from the lead training. We'll go over this when we come back from the break, okay? And then we pipe this. Remember that when I said when you are performing the feature engineering, we use the step functions. Okay, under the recipe, we use step functions. You see this one. Okay, we use the step functions. Okay, so there are so many step functions we'll be using. Okay, so let's go and use step. So we pipe this into step log. Okay, so as soon as you bring step, it knows that you want to do some feature in the engineering. But here, we want to apply a logarithm scale to a particular column. Okay, so what do we want to do? So we need to specify the column. So we use the total time column. Okay, so that is the total time. What do we want to do? We want to convert all the figures to base 10. Okay, let's call this leads log. Recipe. Okay. All right. So let's run this. Call this and see. So it gives us information that the logarithm transformation is on total time, right? So here it tells us that we have one outcome variable and 6 predictor variables. Okay, so this is the variable by row, one outcome variable and 6 predictors. Okay, so let's explore the summary. Okay. We can take this. We pipe that into our summary. Let's run it. So here you see that total visits is in the predictor row. Total time is a predictor. Pages per visit is a predictor. Total clicks is a predictor. Lead source is a predictor. GH location is also a predictor. And then we have one outcome variable. Yeah. Okay. So I think let's stop here. When we come, I'll just go over it and then we can continue from here. Okay. So please take a break and then we come back at 10:30. Okay, or 10:32. At least 2 minutes. Okay. All right. We'll see you soon.
Anna,
Yes, go ahead.
please, I'm going through the table, but I've realized that the total clicks too, the values are a bit higher.
Okay, don't worry. Let's do one step at a time. Okay.
Okay.
Let's finish this. We can also go back and then do that one too as well. Okay.
Okay. Okay. Now, thank you.
Okay. So we have a correlation matrix. So we have total visits, total time, pages per visit, total clicks. Okay. So you know how correlation matrix works. So that diagonally you can see 1, 1, 1. That is the relationship between a variable and itself is 1. Okay. So we see total visits as against total time, it's 0.006. Total visit as against pages per visit is 0.46. Okay, this one. And then total visits as against total clicks, okay, 0.45, and so forth. All right. Now, you will realize that there is a very high correlation between total pages per visit, okay, and then total clicks. Okay, you see here, it has a very high correlation. That is 0.96, which means that as the number of pages per visit increases, total clicks also increases. Okay, and when you have variables that are highly correlated within the model, it tends to give you problems. Okay, you tend to have overfitting and stuff like that. So as much as possible, you want to have predictors that are not correlated. Okay, so this is a clear issue of multicollinearity, if you remember. All right. So one of the feature engineering steps we could do is to deal with the issue of multicollinearity and remove variables that are highly correlated. okay, so that it doesn't create problems. So if you know one, you can know the other. Okay, we know that pages per visit and total clicks are highly correlated. So if we know one, then we know that the other one too will be behaving in a similar fashion. Okay, so let's see how we can deal with removing multicollinearity, which is also another form of feature engineering. Okay. So let's remove multicollinearity. So we have our list training. Okay. So the correlation matrix give us how these are related. So let's see how we can remove it. Okay. So we have our recipe function, and within this recipe function, we know the equation, okay, for the regression, for the relationship. Okay, so we are taking all the predictors. Okay, and then we are taking the data we are taking is the least training. So data is equal to least training. Okay, and then there's an N here, and then we pipe this into a function called step call. Remember, the feature engineering functions we use in recipe are all steps, okay? So step call, okay? Please pay attention that this is double R, okay? Step call. So we have here our total visits, Let me just copy this. Total visits. We have our total time. We have our pages per visit. And then we have our total clicks. So what it will do is that it will go into these variables, find out which ones are correlated, and then it will take them out. Okay, so the one that has the least influence, it will take it out, right? So basically, what we have to do here is to specify the correlation threshold. Okay, so we need to specify the correlation threshold. So here we can set a threshold of, let's say, 90%, 0.9. So what this means is that this 90% we are using is an absolute figure, or 0.9 is an absolute figure, which means that any correlation that is above 0.9, okay, if you find a relationship, because there are so many relationships, okay, if you find a relationship that is above 0.9, take it off, okay? We can reduce it to 80. It depends upon you, okay, and what in the context of the work you are doing. Okay, so you set the correlation threshold. Okay, so it is this threshold that the step call is going to use, and then if there is any issue of multicollinearity, it will remove that. Okay. So let's name this object list call recipe. Okay. Okay, so let's run this. Okay, there's a gap here. Training.
It's in the spelling. It's missing an I.
Yeah.
Yeah.
Thank you. Okay. Okay, so let's see what we have here. So it tells you that correlation filter is on. Okay. So total versus total time pages per visit. So it's considering all this. Okay. So later when we print the variables, you see that the ones that are highly correlated will be removed. But before we do that, this is a long route, but I wanted to show it to you. Okay. So alternatively, you can get the same results. Alternatively, we can get the same results by using what we call the all numeric. So let's copy this. Just copy the whole of this. I'm gonna put it here. Instead of using the individual columns, okay, we can say that all numeric. So that means that it will go into the various variables, everything that is numeric. Then it will check for the correlation and then remove the ones that are highly correlated. But be careful, when we use the all numeric, if the outcome variable is numeric, then we need to ensure that we bring minus all outcomes so that it doesn't transform. What we don't want to do is to transform our outcome variable. Our outcome variable should stay the same. So, but if the outcome variable is numeric, then we have to bring minus all outcomes. Okay. All right. But all right, we will get there. Okay, we'll get there. So just for you to know that if our outcome is numeric and then we are using all numeric, then you need to tell the model that no, don't process the outcome. Okay, don't process the outcome, which is numeric. But in this situation, our outcome variable is categorical, so we don't need this. Okay, we will take another one that has categorical and then we'll bring this. Please, is it okay?
Yes, sir.
Yeah, okay, good. All right, so we do that. So all numeric, and the advantage of using this is that if you use all numeric, for instance, and then the names of your variable change, it will not affect your feature engineering. You can still run it. Okay. Unlike repeating the individual names, if the names of the variables change in future, you need to come and then change it here as well. But if you do this, it covers everything. When the names of your variable change, it will not affect your code. All right. Okay. So that's the advantage of the all numeric. Okay. So this one you write less and then you achieve the same. Okay. Basically the same thing.
Hello, Nana.
Yes.
Please, with the threshold there, is it only 90 you can set to, or you can set it to any?
No. You can set it to, I explain, you can set to anything. So if you set it to, let's say 80, it will do the correlation matrix, and then any figure that is above, and I told you this is an absolute figure. So any figure above 90 or more, it will deal with the multicollinearity, or negative 0.9 or less, it will also deal with the multicollinearity. All right?
Okay, thank you.
Okay. So now that we have set this, let's apply it to our train data and also to our test data. So apply transformation to train test data. So we do that by using the prep function. So this one has the multicollinearity sorted out. Okay, so we can copy this and then we pipe this into our prep function. We pipe this into our prep function, and the training argument is equal to leads training. Leads underscore training. So what this does is that it transforms the training data set. Okay, and then we can also pipe that into our test data set, and it will also transform our test data set by using the big. So new data. Go to leads testing. If you wanted to find out the one for the training data, we'll set it at null. Okay, but it has stored everything in memory already. Okay, so even if you don't set it at null, it has done that in memory. Okay, so let's run this. Yeah. Let's see the results. Okay, so let's see our results here. So now you see that we have our total visits, total time, total clicks. You see that pages per visit has been removed. Okay, it is not part of our final printout because the issue of multicollinearity has been dealt with. Okay, any question? Any question? Okay, let's do another feature engineering, and then we bring everything together. Okay, let's deal with normalization. Okay. All this we've done. Okay. So another common task is centering and scaling numeric variables, okay, which we know as normalization. We did it last time, all right? So basically what you want to do is to subtract the mean and then from the variable, okay, the numerator, and then divide by the standard deviation, okay? This should be familiar to you when we did mathematical foundations, okay? So this helps you to get it helps you to get like get to a situation where your mean is 0 and then your standard deviation is 1. All right. Okay. So when it becomes that way, it's very easy to do comparisons. For instance, if you look at the total time, that was 1,273, for instance. Okay. And then we normalize it. Okay. We subtract the mean and then divide by the standard deviation. What it does is that it gives you 1.19, okay? And which is easy to interpret, okay? So here, you know that this particular customer spent 1.19 more times than the average customer. So it's very intuitive, okay? So one of the ways by which you can make your data gain more insight is to normalize your data, and especially if they are in different units and stuff like that, okay? You can normalize them so that you can do comparisons here and there. Okay, so let's see how we do this in our studio. Okay. So let's bring our what we have here. So let's bring this again. So now we have our step core that has dealt with the multicollinearity. From this. Okay, we have our step core that has dealt with multicollinearity. What we can also do is to add another step which will normalize the data. Okay, so we can pipe this further, okay, into what we call the step normalize. Okay, step normalize. So it will have it here. Step normalize. And then what do we want to do? We want to normalize all the numeric variables. So all numeric. Okay. It's a function. So let's name this least norm rec. Okay, so that's the normalization. Let's run this. Let me bring this down a bit. Okay. I think I typed in between some. So I think it should, this one should go up a bit. That's okay, so we have here normalized. So let's run this. So after we run it, and we can pass this to our prep and then to, so this pre-processing, okay? So we can pass this to our training data sets and also to our testing data sets, okay? So here, apply pre-processing steps or pre-process transformations to training data. Okay, and normally we use the prep function for that. Okay, so let's take our normalize. So this includes, so here, this least norm rec includes the feature engineering for multicollinearity and also normalization. Please, do you agree? Hello?
Yes, Doc.
Okay, so let's move on with this. Okay, so we have this. Let's pipe that let's pipe that to our prep. So our training argument here is equal to leads training all right. So we can pipe this to our big function so that we can print it out. Okay. So big new data is equal to null. So the null deals with the training data set. Okay. So let's apply the transformations. Okay. So this is the training data set. Okay. So we can also apply it to, let's apply it more importantly to our test data set. So when you do all this, especially when you get to, let's say, 156, it would have saved it in its memory. So this one, this big new data is equal to null. Whether we run it or we don't run it, it will apply it to the training data set. Okay. But this, I'm running it so that you will see how it's done. Okay, so let's apply it also to the new data to our test data set. But that's what we are going to use to predict, isn't it? So that's our leads testing. Okay. So let's run this one too. So this one gives us our normalized. So here you can see that pages per visit has been removed. The issue of multicollinearity has been dealt with, and also the rest of our numeric variables have been normalized. Okay. Any question? Any question? Yes, yeah.
No, please. I just wanted a little bit of clarification. Why do we always apply it to the original data, that's the least training? For instance, when we did the scaling, we reduced the total time. Why didn't we use that variable we created for that within all these, but we always refer to the original data sets?
Okay, so when I was doing the individual ones, I did it individually so that you see how it is done. All right.
Oh,
okay. But now it's like we are putting everything together.
Okay.
So how the thing works is that you need to define the kind of transformations that you want to do in the recipes. After you have done that, then you apply the transformation to your original training data set. Have you seen? And then your test data set. Because your train data set and your test data set should be the same so that you'll be able to do your prediction.
Okay.
All right.
Thank you.
Okay. Right. So here we've been able to deal with multicollinearity. We dealt also with and we've also been able to deal with the normalization. Okay. All right. Any question? Any question? Any question? Okay. If time permits, we'll take one thing that will put everything together. But before then, let's see how we can pre-process nominal predictor variables. So you have to pre-processing nominal predictor variables. So the variables that we did earlier on were numeric predictor variables. What about if you have nominal? Remember a nominal data. A nominal data is a categorical data, but it is not in order. Okay? So yesterday when we looked at job satisfaction, excellent, good, excellent, very good. These are ordinal data, okay? Predictor variable. So that one is in order. But if you have like male, female, and stuff like that, yes, no, it is not in a particular order. All right. So these are nominal data. So if you have such in your data, okay, as predictor variables, how do you perform feature engineering? Okay. So let's see this. Okay. So one of the ways is to use what we call the one-hot encoding. Okay. So nominal data must be transformed to numeric data for modeling. So let's say you have finance department, marketing department, and then technology department. All right. For you to determine whether you are dealing with the finance department, this for argument's sake, okay, it has to be one. Okay. So if it is one, that means that if finance and finance is one, that means that you are dealing with finance department. Okay. If finance and marketing is 0, marketing and technology is 0, that means that finance is 1. So each row should be equal to 1. Okay. So if you like compare, you want to identify marketing should be 1. Okay. So while the other departments are 0. If you want to identify technology, the column for technology should be 1, but the whole row should be 1. Okay, then we know that we are dealing with technology, but you are not dealing with marketing and then finance. So at the technology row, technology department will be 1. At the marketing row, marketing will be 1. At the finance row, finance will be 1. Please, are we okay with this one? Are we okay with this one?
Yes,
So,
sir.
so this is the one-hot encoding, okay, of identifying or transforming numeric ordinal variables, okay? Because it has to be, we need to use numbers so that the machine learning algorithm will be able to do it, okay? Another way by which we can transform nominal predictors is to use what we call dummy variable encoding. So the first one where we have finance is 1 and then marketing is 0, okay? It's a bit redundant. Why? Because if we have a situation where marketing is 0 and then technology is 0, then invariably we are talking about finance. Is that not it? Okay. What do you think? If let's say you have not been told anything and then marketing is 0, you know you have only 3 departments. Marketing is 0, technology is 0. Then you know that it will be finance, is it not?
Yes.
Okay, so that is the idea behind the dummy variable encoding. Okay, so here it reduces the number of columns. Okay, here we have 3 columns. Here we have 2. Okay, so it will fix the first one 0. Because it is 0, we know that it's finance. All right, and then marketing will be 1, and then technology will be 1. Okay, so this is a dummy variable encoding, and this is what Tidymodel uses to do its feature engineering on nominal predictors. Okay, so let's see how we can use that in our R. Let's go to R. How we use our dummy encoding, okay? So by default, that is what Tidymodel uses. Okay, so we have here GH location, isn't it? So if we want to create this, we want to create, so we have lead source and also GH location. Okay, so let's see how we can transform this. All right. So let's have recipe package. Recipe package. You have the purchase. Yes, yeah. Are you asking a question?
Yeah.
Hand is raised. Yeah.
Do the columns need to be factored before you'll be able to work with the encoding, or if they are all in like test?
You see that it has already done it.
Oh, okay. Yeah, so that's what I'm asking. Do we always need to factor those columns before? Because I see that.
So what this one does is that it takes the categorical variables and then inwardly does the factoring. So you don't really.
Oh, okay. Thanks.
All right. So yeah. So we have here the tilde dot. Okay. So our data is equal to leads training. Is training. Let's pipe that. So we pipe that into what we call step dummy. Okay. Step dummy. So here, based upon what we've learned already, instead of naming all of them, okay, why don't we do all nominal? Okay, we pick all nominal. All nominal. Okay. So it will pick the lead source and also GH location. These are the nominal ones. Okay. All nominal. And also watch out for this here. Remember that our outcome variable is also categorical. Okay. And then we don't want it to be transformed. Okay. Therefore, we should remove it from the all nominal. All right. So here we bring minus all outcomes. Okay. Minus all outcomes. And that's so what you are telling the model is that don't pre-process the outcome variable, which is purchased. Don't pre-process it, but pre-process any other nominal variable you find. All right. Okay. So let's pipe that. Let's pipe that into our prep. Where we have training is equal to leads training. And then we pipe that to our big function. Yeah. Where we have new data. New data is equal to leads testing. Okay. So we apply the transformation to both our training data sets and also our test data set. Okay. Let's name this dummy so that we can bring it up. So what do we have here? So now we have it gives us a table, okay, of just a minute. So you can see that the nominal variables have now been converted into ones and zeros. Can you see? Okay. It has been converted to ones and zeros. Okay. For location, lead source. Okay. For all of them. So now, so this is the dummy hot encoding. All right. So based upon this, we can use it to do our prediction. Any questions? Any questions? So now we've seen how we can apply logarithm scale, okay, as a feature engineering stuff. We've seen how we normalize our data. We see how we remove multicollinearity, and then we see how we deal with nominal predictor variables. Okay. The other feature engineering stuff you might need, but this more than enough to get you started. Okay. Any questions? Any questions on this? Okay.
Hi, Nana.
Yes.
So you said the output can be different because of the seeds we choose, right? And that is normal.
Slightly different, but basically our
Slightly different.
interpretation is going to be the same, whatever we predict. And because of what I was explaining earlier on, sometimes the choosing of your 70%, your machine, the 70% it picks might not be the same number of variables. It might not be the same type of variables that it will pick for mine, though the numbers will be the same. Have you seen? That's why you might have slight
But my problem is, you see
yeah.
how yours is having the output is 389 more rows and 7 more variables.
So which
Unfortunately, I
means
am getting 6 more variables.
you are getting 6 more variables. Okay, so what was the
Yes.
total number of your
Rows
yeah, the total number of rows was the same.
was the same, yes.
Okay, and then so do a glimpse and then see.
Yeah. Okay.
Do a glimpse and then let's see the number of variables you have. So here I have 12, 399 by 12. So check
Yeah, I
that.
also have 12.
Yeah, so
399 by 12.
your number of columns is the same.
Okay.
All right.
All right. Thank you, Nana.
Okay. All right. Yeah. Any question? Any other question?
So
what? Any question? Was somebody asking a question? Okay. So what I want us to do, let's put everything together and do one complete modeling workflow. Okay. We'll be moving very fast. Okay. So let's do one complete modeling workflow. We want to bring everything we've done together. Okay. So let's use our telecom data, the one that I sent to you. So that you have a rounded view.
Hi, Nana.
Yes.
I understand that it will be good to consolidate all of this so that when you are sending it to us later, it will be round, it will be one. But can we start the new one in a new script? Like afresh?
Hello?
Hi.
Please, can you hear me? There is power outage here, so can you hear me?
Yes.
Okay. Nancy, you were saying something.
Sorry, I was just asking if we could start the new project in a new script.
Oh, okay. No problem. We could do that. But
Thank you.
currently, I don't know whether I have enough power to be able to. Because I don't know. For those in Accra, I think Anyone in Accra on the platform? I don't think so. I think there's a major power outage here in Accra. So let me see if I can still connect. Just a minute. Okay. Let me just use my MTN as hotspot. I'll be with you in a minute, okay?
Okay.
Okay. Since I've connected our phone. Okay. So what I'll do is that let's import the telecom data set. Can you hear me?
Now your voice is breaking very bad.
Okay. Just a minute. I have to go off here. Is it better?
Yes, please.
Is it better? Okay. Okay, so let's Okay, let's read this. All right. So we've imported our data. Okay. So let's have a look of the program of the variables. So we have whether people have cancelled their service or not, and the type of service they are on, average data per gigabyte, all this telecom information, internet service contract, month with company, monthly practice. All right. Okay. So what we want to do is predict whether somebody will cancel that or not. Right? So basically, we'll be using our data. So let's do our data partition. Okay. So let's have telecom splits. So we have our initial split. We are taking it from the TD data set. Okay. So this time around, let's make our proportion 80%. Okay. Then our strata is equal to cancelled service. Right. So let's look at this. So let's populate our training and test data. So TC training, TC training, we are taking it from TC split. Okay. Let's pipe that. Let's pipe that to our training function. the same thing for our training, our test sets. I'll just change this question. Okay, then this one is piped into the testing function. Okay, that's one. So now we have our trained and test data. Okay. Let's specify our model. Okay, so because it's a categorical outcome, we're going to use logistic regression, isn't it? So T, logistic. Okay, so we'll use logistic regression. Package. Type that into our stats engine. Okay, and this one is regress, logistic regress, so GL represented. And we pipe that also into our stats mode, which is classification. Okay, so let's run this. Good. Okay, so let's build our feature engineering pipeline. Okay, so we want to remove all issues of multicollinearity. We want to normalize all our numeric variables and also to dummy encode our nominal variables. Okay, so let's do it step by step. So use the recipe, transport service. Okay. So that everything is into it. But our data is equal to TC training. We type that into our step function. So let's remove collinearity step call. So we want to take all numeric. Okay. And then since all numeric, so we are okay with this one. Fine. Function. We type that. We type that into let's normalize all numeric. Step normalize. All numeric. Function. Okay, and then we type that also, and then dummy encode all predictor variables. So step dummy. All nominal. And since the outcome variable is also nominal, we need to remove it from pre-processing. So we deduct all outcome. Let's name this recipe. Okay, so let's train our recipe prep function. So we take our TC recipe, then we train it. So TC recipe, we type that into our prep function. Here, training is equal to TC training. So let's name this TC training prep. Okay. So once we have trained this, let's apply it on the trained data. Apply trained transformations on training data. So we take prep, then we pipe that to our big, the new data equal to null. Remember? So that one does apply the transformation to the training data. So let's make this TC training prep. Okay? On this. So let's apply it to the test data. Now, let's copy this. This training. So this one will be testing data set. So we just change this to test. Please, I'm sorry, GC testing. Then let's change this testing. Run this. Okay. So now we've applied all the transformations to our training data and also our test data. So now let's do our model setting. So here we take our TC logistic model that we created. TC logistic model that we created. Okay, and then we pipe that. We pipe that to the fit function. Okay, our cancelled service. So let's give the relationship between the outcome and the predictors. But now our data will not be the training. It will be the training prep, the one that has been pre-processed. Okay? That's the difference. So we still see training prep.
Hi, Nana.
Yes.
Are we like how do I say altering the column name? It's cancel service, right?
Yes.
Or just
You
typing
said the
cancel
cancel
is
service.
okay.
No, it came with the data. So let's keep it at that. Okay.
Okay.
You mean that 1L?
No, it's cancel service, right?
Yeah. Oh, so
Or
okay,
just
sorry.
cancel.
Cancel service. Oh, thank you. Thank you. Was that Nancy?
Yes, then.
Okay. So cancel service. Thank you. So cancel service. Okay. All right. So so we've fitted the model. Let's do. Okay. So we fitted the model. Good. So let's do our predictions. Let's do our class predictions. The model that we fitted, let's give it a name. TC logistics fit. All right. Everything is coming together nicely. So let's do our class predictions. So we use the predict function. We did all this yesterday. Predict function, and then we are using the TC logistics fit as our data. Okay. And then the new data is our TC testing prep. Okay. That's where we have the pre-processing stuff. Okay. And then our type is equal to class. That's for classification. Okay. So let's name this class predictions. So we have run our class predictions. Let's run our probability predictions. We'll put everything together. Okay? So these are probability threshold. So this is from. So we change this to from Right. So we change this to top. Right. So now we have our class predictions and also our probability prediction thresholds that were used in making the prediction. Okay. Let's combine the results now. So we have TC testing. We have TC testing, we type that. And then we select the actual value for cancel service. And then we pipe that into buying code. Then relate that to the class predictions and then the probability predictions. Okay. So let's call this TC result. Okay. Good. So now we have fitted the model. Let's see how the model is performing. So model evaluation. So let's take our TC results and do a confusion matrix. So conf map. So our confusion matrix here, the truth is equal to the cancel service. And then the estimate is equal to the class predictions. So dot red underscore class. Yeah. So on this. Okay, so we have a confusion matrix. The true positive is 51, true negative is 113, false positive is 17, okay, false negative is 15. So let's look at our accuracy. The accuracy of the model. So we have TC results. Okay, truth is equal to cancel service. Let's release it. And then our estimate. Estimate is equal to dot red underscore class. So that's our accuracy. So accuracy is 83%, or approximately 84%. Okay, which is good. accuracy metric or parameter. Let's look at sensitivity. So yes, copy the whole stuff. Yeah, let me run this quickly and then I'll answer that, and that the laptop will go off. Then I'll answer your question, okay? Okay.
Okay,
So
then.
let's.
I was just saying that we forgot to set the seed at the beginning.
You said I forgot to.
We forgot to set the seed.
Okay, for this one. Okay. When I finish, I can set it and then run everything again.
Okay.
Okay, so our sensitivity here is 77%, which is, so when it comes to predicting positive cases, it's quite good. Okay, so let's look at our specificity. How we predict negative cases, whether somebody will not renew their contract. Specificity. So we change this to spec. See what this one is giving us. Wow, so this is giving us, our model is really doing well. It's giving us 87%. So in spite of the fact that the sensitivity is doing well, 77%, our specificity is even doing better. All right, so the model is good. So let's look at how we can plot our ROC curve. So we take our TC results. We pipe this into our ROC curve function. Here, the truth is equal to cancelled service. The truth is equal to cancelled service as compared to dot thread. Let's call yes. So that is the false positivity rate, okay? And then we pipe this to autoplot. Okay, beautiful. So our ROC curve is on the left-hand side, okay, which is good, but we don't know the actual number, okay, because we want a number that is very close to 1. So it is the AUC curve, the AUC, area under curve, that will give us the number. So let's calculate that. So let's take our TC results, yeah, okay, everything, this one. I'm going to put this guy here. So now we change this one to rock AUC, okay? Rock AUC, that's what we need. Wonderful. So our AUC is giving us 82%, 88%, which is very good. So our model performance is very good. So which means we can basically use this model to predict whether a customer will cancel their contract or not. Any questions? So we've taken a typical workflow where we partition the data, we apply feature engineering, okay? We dealt with issues of multi-collinearity, we normalize all numeric variables, and then we also dummy encoded all the nominal predictors. After that, we pass all these ones into the prep function, okay? And then applied the trained data to the training set and also the testing set. So they all took on the pre-processing step that we've done. That is the normalization, the multicollinearity, the dummy encoding. All right. So it took all of that into consideration. So it applied the transformations to both the training data sets and also the testing. And based upon this, we fitted our model, okay, and then we plotted the ROC curve, which was quite good, okay? And then we calculated the accuracy of the model, which was quite high, okay? And then we looked at the sensitivity and also the specificity, okay? Which are also very good. And then we looked at the overall area under curve, which also gave us 88%, indicating that our model is very good to be used to prediction. Okay. So that's a complete workflow. Any question? Yes, Michael.
So, sir, my question is that let's say after building this model and you have another data, do you go through the same process or there's a shortcut where you can just upload the data and then maybe...
You mean the same data that has come to be added to this?
No, let's say we build this model from the data that we've been given and we get a new data containing similar columns and everything.
So the idea is that new data will be like your new test data, isn't it?
Yes, please.
So you've trained the model already. So you can apply that and then see the results. So basically what this is that based upon the information that we have, if somebody is coming to apply for a new contract, we can predict whether this person will cancel their contract or not. For instance, if you've been with somebody for a while, and then we know all the attributes, okay, like the contract type, the number of gigs they've been using and stuff like that. Okay, we can have an idea as to the time that person might cancel the contract based upon the model that we've built. So in such situations, when we are able to identify such people, we can do special promotions for them, anticipating that they are going to cancel their contract. We can, do special promotions for them so that we continue to keep them. Okay. So when you get new data, this new data can be your test data. Okay. And then you use it to do your prediction. Once you've trained the model already. Does it make sense?
Yes, sir. But I was thinking that when you finish building the model, there should be a way of maybe putting it in a shortcut or something that the new data you get, you just upload the data, you click on one button and it automatically gives you the prediction.
Yes. So if you get new data, you've trained it already. So whatever new data you get is now going to be your test data. So you just put it into where you have the test data and run the model, you get your prediction.
Oh, okay. Okay.
You remember that's why we said that when you are doing the feature engineering, it's better to use all numeric and then all outcome so that when your variables names do change, it doesn't affect the coding that you've done.
Yes, sir.
Yes, Francis.
Yes, Nana. I see from here you split the data before doing the feature engineering. My question is, can we do the feature engineering on the full data set when we are done with that before we come splitting it to training and testing?
So you do all the feature engineering, everything on the data, and then when you finish, you split it. I think it's going to work.
Yes.
I think
Okay.
it's going to work.
All right.
All right. But the industry practice basically is that you do all the cleaning and everything, all right, and then you split the data, and then you are. So basically, what this one does is that after you split your data, and then after you split your data, okay, and then you apply the transformations to the test data and also to the training data, okay. If we are to answer the question that was asked previously, let's say we get new data, okay. If we get new data, how are you going to train it? Because you use both your test and then your train data to do the training for the first one. So I don't know what I'm
No,
getting to.
no,
So
not in that case. You clean the data, you set the features, you engineer the features on the full data set.
And then when you finish, you partition
Then
it
you
and then
you split it into training and
that's
testing.
also fine. That's also fine.
Okay. Okay. And to the question that Michael asked earlier on, I don't know. Yesterday I asked if we could see the model estimate. I don't know. I asked because I also had that in mind. If you know the model estimate and you can copy it into an Excel, so that when you get a new data set, maybe just one person coming on board, you can just use that one person and input it into the Excel estimated model. Then you get the prediction.
No, the prediction. So the prediction, will it be after you've done the feature engineering?
Yes, after you've done everything, you've trained the data and you've seen the estimated model.
Oh, I get you. What we are trying to do here is that everything is being done within. I answered it yesterday. Everything is being done within the context of Tidymodels. So Tidymodels, we can't do that, but there are so many ways in R that you can just use to get your model for the logistic regression. You know that.
Yes, yes, I get it.
So this one is within the context of Tidymodels. It has its own limitation.
Okay, yeah, sure.
Yeah, guys, please ask all your questions before my laptop goes off. We are still having power outage. But please, have you gotten a gist of what the whole thing is about?
Yes, yes, sir.
Yes, sir.
Mine was a follow-up to Michael. So just a clarification, if you get a new data set, you have to clean it same way you've done the test data in order to apply the model.
Yes, of course, you have to clean it, and then the transformations have to be the same. Other than that, you will not be able to predict.
Okay, that's true. Thank you.
Okay. All right, guys. Thank you so much. Please, is it possible? We have a lot to cover. I really want you guys to be firmed up. Okay, and the timetable. I'll be putting a lot of stuff on you if we cramp everything together. So I was thinking, is it possible to have a meeting during the week, one slot during the week, and then we see how next weekend goes, whether we'll be able to finish or we need more time.
I think
Okay,
1 week will be fine.
So please, just Ransford, if Ransford is here, can you, speak among yourselves and let us know the day that will be suitable for you. Let me know way ahead of time, okay, so that I can prepare. So we can do another model during the week. Next week will be fully loaded. And then we see whether we can finish. If not, then we strategize as to what to do. Okay.
All right, Nana.
All right. Okay. Thank you very much. Have a very wonderful afternoon. Here in Accra, it's raining very heavily.
And just a quick one.
Yes.
Please, can you get us another data set just for practice?
Yes. I can send you another one. Okay.
Thank you.
Do you work in the bank? Let me send you something so that you predict whether somebody will be approved for a loan or not. You say? Okay, so I'll send you.
So wait for it so that we can practice along.
Okay, I'll send you another data set for loan approvals. Okay.
Nana, if you have something for visa application too, you can.
But that one, the embassy would not give us the data. It would have helped very much. So if you become a connection man, then you run the model and then you see whether this person will get the visa or not.
Exactly.
That will affect the amount of money you charge.
Nana even says, send us sporty bets. Send us sporty bets.
Okay, guys, have a wonderful one and then speak to you soon. So kindly let me know the time you want us to be during the week. Okay. Thank you very much.
Thank you very much, sir.